Good evening, my dear students. In this lecture, I would like to give a brief idea about moment area method application for finding the slope and deflection of beams. Here, first of all, we must understand what is slope and what is deflection of beams. See, first of all, let us see the deflection of beam. Here you can see that here it is a, see this, it is a beam. Beam, what is beam? Beam is a horizontal structural member that is subjected to transverse loading. Here it is a simply supported beam. Here these are the supports here at the ends. Here is there any load is there? No, load is not there. Initially, the neutral axis of this beam is horizontal exactly, right? Now, so it is what we can say, it is unloaded beam. Why? Because there is no load is acting on the beam. Now, suppose if the beam is subjected to a load like this, here you understand the initially before the loading applied, the neutral axis of the beam is straight horizontal, exactly straight horizontal. Now, whenever if you apply a load, then what happens? Because here you see that it is a simply support beam subjected to point load W at its center of the beam. So then you understand there is a deflection of this beam. This is a deformed position of the beam. Earlier, there is no deformation at all because there is no load is acting on the beam. That is undeformed position of the beam because no load is acting on it. But in this case, you see that there is a load W. Because of the load applied, what happens? The horizontal neutral axis takes a curved form. You see this is a curved form, right? So this is what you can say, it is a deformed beam position. It is a deformed beam position. I hope you understand. Next. So it's a loaded beam. Now, here it is very clear, you can understand it is a simply supported beam. Here, one support is here, another support is here. Here it is subjected to point load W at its center. For understanding purpose, I have taken the simply supported beam. Any beam we can follow. Here, see that there is a, after load is applied, you can see that there is a deformed position of the beam like this. This dotted line indicates the deformed position of the beam. So the deformed position of the beam, that we can call it as elastic curve. So it takes the curved form, that we can call it as a elastic curve. I hope you understand. Next. Here it is a cantilever beam. Here also you see this, it is a, before loading it is horizontal. Whenever it is subjected to load, here the load every time load need not be a point load, that may be UDL or UVL or point load, whatever it is. Here the beam takes the curved form. You see this is a deformed position. This is the deformed position of the beam after loading, right? So this dotted line, you can see this is the elastic curve. We can call it as elastic curve. Now in simple, we can understand here A to B. What is this one? This dotted line. It is a undeformed position of the beam when there is no load is acting on it, right? Once load is acting, it takes the curved form. It takes the curved form. See this. This is the curved form. You can, sorry. See this? So because of this load, the neutral axis becomes a curved line. You see, you understand the curved line. You see this. This is the curved line. So this curved line, we can call it as a elastic curve. We can call it as a elastic curve. Now, I hope understand. Let me repeat. Before load applied, the beam, the neutral axis of the beam is horizontal. That can be seen here. It is a dotted line. Whenever the load applied, it takes the curved form. This curved line, we can say it is called elastic curve, right? Now we go further. See here, you see from the figure you can see here. What is the point C? It is the point on the neutral axis before the load applied, right? After load applied, then it takes the curved form. You can see that there is a elastic curve is formed. So this point is shifted to point D here. So here you understand there is a vertical distance is there. Vertical distance. This vertical distance we can call it as a deflection. This vertical distance we can call it as a deflection. So what is that? How can you define the deflection? It is the vertical distance that is measured between a point on the elastical. Which one is point? D is the point on the elastical, and the unloaded neutral axis. What is this? A to B dotted line is the unloaded neutral axis. Here you can easily understand the definition of this deflection. Deflection means simply it is a vertical distance between a point on the elastic curve and what is this dotted line? Neutral axis. So this vertical distance we can call it as a deflection, right? Now, here you can see that deflection. What is this point? It is a end point of the beam. It is another end point of the beam as far as simply supported beam is concerned. Here actually there are supports. At the supports, you cannot find any, if the point A is also on the elastic curve, the point B also on the elastic curve. If you see that at point A or at point B, because these 2 points are at the supports, so there itself you cannot find any vertical distance on the elastic. So if you take a point A on the elastic curve, you cannot find any vertical distance. Here at point B also, you cannot find any vertical distance like between C and D. So therefore, finally, what you can conclude that at the supports, the deflection equal to 0. Whatever the support, the deflection must be 0 at that support point. Now, deflection at the support is always equal to 0. You must remember this point. Very, very important. Deflection at the supports is always equal to 0. Here it is simply supported beam. Here it is one support is at point A, another support is at point B. The supports at A and B. Therefore, what is the deflection at A? Deflection is denoted by the symbol Y. YA. What is the meaning of YA? Deflection at point A. So what is the point A? It is a point at which one support is there. So what is the deflection at support? Support point, that is 0. So what about at point B? YB also equal to 0, right? So at point C, you can see it is a maximum deflection. You can see that maximum deflection, right? Now, so this is the definition of deflection. Once again, let me repeat. What is the meaning of deflection? It is the vertical distance. It is a vertical distance between a point on the elastic curve and the unloaded neutral axis. Neutral axis of the unloaded beam, right? Now, come. Now, here, in the case of simply supported beam, you are observing one support is at A, another support is at B, right? So what is this dotted line? It is elastic curve. It is a elastic curve. Here, at the point A, please try to understand. At point A, on this elastic curve at point A, I would like to draw a tangent. Here, what is this line? It is a tangent. This tangent makes an angle with the horizontal neutral axis or neutral axis of the unloaded beam. So that angle we can call it as slope at that point. I hope you understand. Similarly here at point B, I have drawn a tangent. The tangent makes an angle with the neutral axis of the unloaded beam. So that angle we can call it as a slope at point B. So at point A, the slope is denoted by theta. Theta is used to represent the slope. At point A, the slope is theta A. At point B, the slope is theta B. Now, another important point. At point D, it is a dotted line. It is a elastic curve. At point D, what is the slope? So how we are going to obtain the slope? Wherever you want to find the slope on an elastic curve, you have to draw a tangent. At point, if you draw a tangent, what is the angle made with this? You see that there is the tangent appears like a horizontal straight line. This tangent at point D. So this tangent having zero angle with the horizontal neutral axis. Therefore, what is the slope at point D? Because there is no angle with the horizontal. Therefore, we can say that at point D. So that is theta at D. Sorry, theta at C. Say theta C means this point D is actually it is a C point that is represented on the elastic curve as D, right? So theta C equal to 0. What is the meaning of theta C? 0. Slope at point D equal to 0. So here you understand there is a maximum deflection is there, but slope equal to 0. Now, so let's see the definition of this slope. Simple, it is an angle that is measured between the tangent to elastic curve at a point. So you on the elastic curve, you take any point, wherever you want to find the slope, at which point you are going to find the slope, then there itself you have to take the draw a tangent. Here I want to suppose somewhere here I want to find the slope. Then you have to draw a tangent here. You have to measure the angle made by the tangent with the horizontal. That will give you the slope at that particular point, right? Now, the slope is denoted by theta. Already I mentioned. Here theta is the dy by dx. Slope is represented in the form of differentials dy by dx, right? Now, so already I told you there are different methods for finding the slope and deflection of beams. Some of the methods, one is the basic fundamental method, that is double integration method. The another method is moment area method. Actually, today I want to clear idea about the application of moment area method. Before going to for moment area method, first we see what complexity takes place in double integration method. So how the moment area method removes that complexity, finding the slope and deflection. Here, double integration method. Before going to the double integration method, you see this basic differential equation for the deflected shape of a beam. Deflected shape beam, already I told you, deflection is, say, it is an unloaded beam. So once it is subjected to some load, then it takes a curved form like this. This curved line, what you call? It is a elastic curve. Elastic curve, right? So a differential equation, we can use it to represent this elastic curve. So that is very, very important here for applying this double integration method. So what is the basic differential equation of this curve? What is the basic differential equation of this elastic curve? That is m equal to EI into d square y by dx square. This is the differential equation of elastic curve or differential equation for the deflected shape of the beam, right? M equal EI into d square y by dx square. Here, what is that M? Bending moment at the section. E is the Young's modulus of the material of the beam. I is the moment of inertia with respect to neutral axis. Next, what here? Y is the deflection. Y is the deflection, right? Now, can we write like this? EI into d square y by dx square. EI into d square y by dx equal to M. Just I have written the other side. EI into d square y by dx square equal to M. Now, here, if you integrate it, one time you integrate it, you are getting EI into dy by dx equal to integral m dx plus C1. What is the C1? It is a constant of integration, right? Next, here, what is dy by dx? It is slope. That is represented by theta. So EI into theta equal to integral m dx plus C1. So it is an expression for slope. Theta equal to 1 by EI into integral m dx plus c1, right? Now, after getting this equation for slope, now again integrating. So you see that after integrating, what you are going to get ei into, if you integrate again, you will get ei into y equal to integral m dx, double integral m dx plus integral c1 dx, that you are getting integral c1 dx plus c2. So further you are getting in double integral m dx plus c1x plus c2. Here understand, this is y is a deflection. This we can call it as a deflection equation. So here to get this deflection equation, we are two times of integrate. We have integrated twice the elastic equation. Therefore, this method we can call it as a double integration method. Now, listen carefully. You can understand first how to apply the double integration method. Then we go for moment area method. Right. Here you see that E is Young's modulus, I is the area moment of inertia with respect to neutral axis. So E is a material property. Here I is the moment of inertia. It is a geometric property, right? But here M is a bending moment. What about the C1 and C2? These are the constants of integration. How we are going to evaluate these constants of integration? Remember, this is very, very important. To understand the, to find the, sorry, to find the constants of integration, we must follow boundary conditions. Once you understand the boundary conditions, you can easily boundary conditions. So once you understand the boundary conditions, you can easily find C1 and C2, right? So these boundary conditions are actually depending on the type of beam, okay? Now, here C1 and C2 are constant of integration. Boundary conditions. So already I told you boundary conditions are depending on the type of beam. Here, first of all, we can see this is a cantilever beam. Here, what is this? This one, this is a neutral axis, undeformed position of the beam when it is not subjected to any load. Once it is subjected to load, then what happens? It takes the different shape, curved shape. You see that? This is the shape we are getting. This one is, we can call it as a elastic curve, right? Now, so my dear friends, you try to understand at point A, can you find any deflection? Any deflection? Deflection is, what is the meaning of deflection? Vertical distance. On the elastic curve, you take point A. Is there any vertical distance? No. That means at the point A means at fixed support. At fixed support. At fixed support, what is the deflection? 0. Similarly, at the point A, you draw a tangent that coincides with the horizontal line. Therefore, what is the angle made by the tangent with the horizontal? That is 0. That's, we can say that at fixed point, at fixed end, we can say that theta A is the slope at fixed end. That will be 0. Why? Because at the point A on this elastic curve, if you draw a tangent, that doesn't make any angle with the horizontal. The angle between the horizontal line and the tangent, both coincides here. That's why theta A equal to 0. What about deflection? Deflection at A. So what is the meaning of deflection? The vertical distance for a point on the elastic curve from the neutral axis at unloaded beam, right? So here that is a horizontal line. So here there is no vertical distance at point A. Therefore, we can say y equal to 0, right? Now, this is these what are these two? These are boundary conditions. At fixed end, remember this point here, slope equal to 0 and deflection also 0. In the case of cantilever beam, it is a cantilever beam, right? Now come. So at the fixed support, this is fixed support. And here it is a free end. There is no support there. It is B is the free end, A is the fixed end or fixed, it is the support, is fixed support is there. Now, slope at A, already I told you slope at A, that is theta A equal to what? 0. Theta A equal to 0. Now, what about deflection at A? Ya equal to 0. Ya equal to 0. So what are these? These two are the boundary conditions. While analyzing any cantilever beam subject to any type of load, you must follow these boundary conditions to find what is the purpose of these boundary conditions, to find the constants of integration C1 and C2, right? Now, this is about the boundary conditions regarding cantilever beam. Now let's go to another beam, that is simply supported beam. Here you see that it is simply where are the supports? At A and B, supports are there. Simply supported beam subjected to what is the span length? That is L. So exactly at midpoint there is a load, point load W that is acting. Because of the load applied at the midpoint of this beam, simply supported beam, you can see that there is a dotted line here. This is the elastic curve, right? Now at the support, do you find any vertical distance? No. That means what is the deflection at point A? Ya equal to 0. What about at point B? Here also support is there. One point you must remember, wherever the supports, there itself deflection equal to 0. So again, Ya equal to 0. What about the deflection at point B? That is also 0. So these are the boundary conditions for the simply supported beam to find the constants of integration C1 and C2, right? Now you can see at the left support, what is the deflection? 0. What is the Ya equal to 0? That's why what is the deflection at the right support at point B? Yb equal to 0, right? So to analyze simply supported beam as well as cantilever beam, you must follow these boundary conditions. So the left side you can see cantilever beam. What are the boundary conditions there? At the fixed support, slope equal to 0, deflection equal to 0. In the case of simply supported beam, at the supports, deflection equal to 0. At left support, deflection equal to 0. Similarly, at the right support, deflection also equal to 0, right? You remember these boundary conditions. Now, let's proceed for application of this double integration method first, and then we go for moment area method. Now, slope and deflection of cantilever beams. So there are different methods are there. So in this lecture, we will focus on the two methods. One is the double integration method, another one is the moment area method. See here, a simple case for understanding of this methodology, I have taken a simple case. What is the simple case which I have taken here? Cantilever beam subjected to point load at its free end. That means you see that it is a cantilever beam. It is a fixed end. It is a free end. Here, where is the load? Load is acting at the free end. So this length of this beam, let us say L. So very simple case. A and B. So if the point load say W, that is acting on the beam at a free end, right? So now our task is to find the slope and deflection for this cantilever beam subjected to point load W at its free end, right? Now, so first we will follow this double integration method and then moment area method. First, you see the actual procedure for adopted by this method, double integration method. So after understanding the complexity in this, how the moment area method reduce the complexity. Very simple, we can find, right? First, you see this. Here it is a cantilever beam. It is a fixed end, fixed support is there. What kind of support is there? Fixed support. At point B, there is no support at all. It is a free end, right? Now, it is subjected to point load W at its free end. Now, let me take a section. You see that it is a section. I have taken a section at a distance at a distance x from fixed end, right? Now I want to, first of all, I want to write the bending moment at the section. How we are going to write the bending moment at the section? Bending moment m equal to, so load into distance. What is the load here? W into, here what is the distance between the section and the load? What is the distance? The total distance is L. This is X. Then you can write L minus X. Next, you must observe whether it produces a clockwise moment or anti-clockwise moment. Here it produces a clockwise moment. When you consider the right part of the section, if it is a clockwise moment, you should take it as a negative. According to sign convention, already we studied in your unit 2 shear force and bending moment diagrams, right? Now, this is the bending. Once we have written the bending moment equation, immediately you can able to apply your equation. What is that equation? Equation of elastic curve or equation of the deformed form of the beam, that is EI into d square y by dx square equal to what? M, right? We can use this equation. So first you substitute the value of m here, integrate once, you are getting the slope equation. Second time you are integrated, you are getting the deflection, right? Now, see this. Here, what is the m? Bending moment at the section. Now, so what is your equation of elastic curve? EI into d square y by dx square equal to m. Let me substitute the value of m. What is that m? M is the bending moment at the section. See this. EI d square y by dx square equal to minus w into L minus x. Further, we can write. So after in 1 year, you see this is a EI d square y by dx square. If you integrate once, d square y by dx square becomes dy by dx equal to, here integral minus w into L minus x dx plus c1 is the constant of integration. I hope you understand how to integrate it. So now after that, you see this integral minus wl, here minus into minus plus w x into dx plus c1. So integrated, you will get minus wl integral dx plus wx w integral x dx plus c1. So further you can write minus wl integral dx means x plus, here w into x dx means x square by 2 plus c1. It is ei into dy by dx. What is the dy by dx? That is theta. So you can write, it is a slope equation, right? Because you can able to find theta. But only the hurdle is C1. So what is that C1? Constant of integration. How you can going to evaluate this constant of integration? With the help of boundary conditions. So what are the boundary conditions we have? In the case of cantilever beam at the fixed end, so what is the slope? 0. So at fixed end means here, once again, it is a fixed end. So when x equal to 0, you can approach the fixed end. When x equal to L, you can approach the free end, right? So at the fixed end, that means x equal to 0, you are getting theta A equal to 0. So here theta, I am putting the values. See, put x equal to 0 in order to find the slope at A, right? Slope at the fixed point. EI into what you can write? Theta A equal to minus WL into x0, because I am putting x equal to 0. Here w x square by 2, there itself x0 square by 2, you are getting 0 plus c1 plus c1. Here what is the theta A? Theta A, what is the meaning of theta A? Slope at fixed support. At the fixed support, slope equal to 0, deflection equal to 0. Therefore, EI into 0 equal to 0 plus 0 plus C1. So what is the value we are getting? C1? 0. So one constant of integration we can solve like this, right? Now, you can easily see the slide, you can understand. Now, the way of finding the constants of integration, C1 is over. One more constant is there, that is C2. Okay, we'll see how to find C2 also. Now, let me repeat this. You see this. So here, after integration, you are getting this equation ei into dy by dx equal to minus WLX plus WX square by 2 plus C1. So to find C1, you have to use your boundary conditions. So if you, okay, already I told you how to find C1. Here, this is what is this equation? It is slope equation. Once again integrate the slope equation, we are getting the deflection equation. This is the deflection equation. In dy by dx, if you integrate it, you are getting y. Here minus WL integral x dx, here integral x dx, similarly w by 2 into integral x square dx plus c1x plus c2. Here further you can integrate it. Integral x dx means x square by 2 minus WL into x square by 2. Here w by 2 into integral x square dx means x cube by 3. So you are getting wx cube by 6 plus c1x plus c2. So here we are having two equations. One is the slope. For this equation 1 represents the slope. Equation 2 represents the deflection, right? Now I want to find C1 first. How we are going to find C1? Using your boundary condition. As far as cantilever beam is concerned, at the fixed end, what is the slope? Theta equal to 0 at the fixed end. Fixed end means here in our example, A is the fixed end, right? Theta A equal to 0. When you are getting theta A equal to 0, when x equal to, when 0, you are getting theta A equal to 0, right? Now, see this. Boundary conditions at the fixed support, slope equal to 0. That means at x equal to 0, theta equal to 0. Theta means what is the theta? Slope. Slope means dy by dx that equals 0, right? Now, you substitute the this boundary condition, you will get C1 equal to 0. Already explained this one, C1 equal to 0, right? Now, the immediate next task is you have to find the final, you have to write the slope equation. What is the slope equation? E into dy by dx. Once getting the value of C1, substitute the value of C1 here. What is the value of C1? 0. Substitute 0. You are getting EI into dy by dx equal to minus WLX plus WX square by. It is a slope equation. So what is the use of this equation? That is very important. What is the use of this equation? It can witness, for your understanding, let me represent EI into, what is the meaning of dy by dx? Theta, that is the slope, equal to minus WLX plus WX square by 2. So here, you see this. What are the variables here? Theta and x. So theta varies with x. What is the meaning of x? X is the distance we are measuring from the fixed end of the fixed support of the cantilever beam. So if x changes, theta changes. So that means it is general equation for the slope, to find the slope of cantilever beam at any distance from the fixed support, right? Now, listen carefully. So what is the another equation? The left side you can see it is the slope. This equation slope represent. What about this one? It is a deflection equation. EI into y equal minus WLX square by 2 plus WX cube by 6 plus C1x plus C2. So of course already you got C1 value is 0. Substitute here. So what is the rest of the integration constant? That is C2. So what here also, to how you are going to find C2? Here also you have to use your boundary conditions. What is the boundary condition you are going to adopt? At the fixed support, already several times I am repeating, at the fixed support, slope equal to 0, deflection also 0. That means when x equal to 0, when x equal to 0, what is ya? You get 0. So substitute here ei into ya. I am writing the deflection equation when put an x equal to 0. So that means this term becomes 0. First term becomes 0 because x square is a 0 square, you are getting 0. Here also you are substitute x value 0. So what are the rest of the terms? Ya equal to 0. Finally, you are getting C2 equal to 0. I hope you understand, right? See how you are getting. So x at x equal to 0, y equal to 0, you substitute the values y 0, x 0. So you are getting C2 equal to 0. So you are having two constants of integration values C1 equal to 0, C2 equal to 0. So here C1, C2 there, C1 0, C2 equal to 0, already got the value C2 0. You substitute in this equation, you are getting EI by 2i. What is this equation? What is the use of this equation? This equation used to find the deflection. Deflection, y, right? Y means deflection, theta means slope. So at any distance x, you can find the deflection with the help of this general equation for deflection equation, right? Now, listen carefully. Slope equation, already I told you it is a slope equation. With the help of the slope equation, you can able to find the slope at any point. It is your cantilever beam subjected to point load W at its end. The span length, you can say it is L. Here end A, here end B. Free end is B, fixed end is A, right? So already you know the value of slope at A is 0 because it is a fixed end. What is the deflection? Also 0. Slope 0, deflection 0 at fixed end. I want to know, please, my dear friends, try to understand. I want to know the slope at point B. Then what I am going to do? How much value I could put x? So put x equal to find the slope at B, you have to put x equal to L. So you are getting, if you put x equal to L, EI into, what is the point B? It is a free end. So here theta B. If we put x equal, x means, what is the meaning of x? It is the distance of the section considered from the fixed end. It is x. If x equal to 0, you are getting A. If x equal to L, you are getting point B, right? So I want to find the slope at point B. That's why I am going to put x equal to L. So EI into theta B equal to minus WL. In place of what I am going to substitute? L plus W into L square by 2. You simplify this, minus WL square plus WL square by 2, you are getting minus WL square by 2. Then what is theta B? Theta B equal to minus WL square by, take EI in the right hand side, you are getting WL square by 2EI. So this is the expression for slope of the cantilever beam at free end when it is subjected to point load at its free end. So this is the expression for slope at a free end, right? Now, right. See, now you can see, you can understand easily EA into theta. Theta means slope, divided by x is slope, minus WLX plus WX square by 2. So I want to find the slope at point B. That means here I want to substitute x equal to L. So then we are getting theta B. So theta B, EI into theta B equal minus WL into L plus WL square by 2. Simplify this, we are getting. So this is the expression for slope at free end for a cantilever beam subjected to point load at its free end, right? Now I want to find the deflection now. Slope already over. Now I go for deflection. So then which equation you are going to take? Slope equation. So deflection equation. What is the deflection equation? This is your deflection equation. EA into Y equal minus W. Already earlier slide you can see this is the deflection equation. Already we derived that equation. So now I want to find the deflection at which point I am going at fixed end. Of course, we know the deflection equal to 0. I want to find the deflection at the free end. Free end means how much value I can put x equal to L. Put x equal to L, you are getting YB like this. So substitute the value x equal to L here, you are getting YB. Then YB equal to minus WL cube by 3I, minus WL cube by 3A. So this left side you can see this expression give you the slope, minus WL square by 2EI. Here right side you can see it is the right side you can see it is the deflection equation, deflection expression. So to find the deflection at the free end, right? Now, so in the representation of the slope and deflection, you see, already I told you, here you are getting the values theta B. What is the meaning of theta B? Slope at point B. What is the meaning of YB? Deflection at point B. So first of all, how to represent slope at point B? Where is point B? Here, this is point A. This is point B. I will change the color of the pen boards. Here it is the point B. This is the point B, right? This is the point A. So you calculated the deflection at B as well as slope at B. At point, what is the meaning of slope? At point B, it is what is this curved line? Elastic curve. At this projection of the point B here, at point B, if you draw a tangent, this is what is this line? It is a tangent. Sorry. This is a tangent. This tangent makes an angle with the horizontal, that is theta B, right? So this is a representation of slope. What about deflection? Vertical distance at point B. So let us say it is B dash. What is the meaning of B dash? It is the point B after load applied on the beam. So this is the vertical distance. This vertical distance give you the deflection. So this is a representation of deflection, right? So now, so far we discussed how to find the slope and the deflection for a cantilever beam subjected to point load at its free end. So here a lot of calculation is there, lot of computation, integration. Of a one-time integration, we are getting slope equation. Second time integration, we are getting the deflection equation. Now, instead of doing all these things, simple method is there, that is moment area method. Moment area method, this method is also called Morse method. So to understand the Morse method or moment area method, you must thorough with the two theorems proposed by Moore. First of all, you see the statement here, Morse theorem 1. So Morse theorem 1 is related to finding the slope. Morse theorem 2 is related to finding the deflection of the beam, right? Here, what is the meaning of this? Right. Now you can see this. Here, the change of slope. See this, the change of slope between any 2 points is equal to the net area of the bending moment diagram. Net area of the bending moment diagram between these points divided by A. So what is the meaning of this? See. Here. So first you understand clearly what is the theorem. The change of, so it give you the change of, not directly slope at one point, not absolutely slope at one point. It give you, the theorem suggests that it gives a change of slope between any 2 points on the beam that will be equal to, more stated that change of slope between any 2 points that will be equal to net area of the bending moment diagram. It is very, very important. So once you have to draw the bending moment diagram, find the area. So that area divided by EI. EI means it is a flexural rigidity, the product of Young's modulus and moment of inertia with respect to neutral axis. So with the help of this equation, you can able to find the slope. Slope direct? No, it is change of slope can find. Now, how to find the slope at the required point? I tell you. Now, so you can represent here. What is this A? A represents, here A is the area of the bending moment diagram, right? E is the Young's modulus, I is the moment of inertia with respect to neutral axis. So with the help of this equation, you can be able to find the change of slope between any 2 points, right? Now, Morse theorem 2. So already I told you Morse theorem 2 related to deflection of the beam. To find the deflection of the beam, you have to use Morse theorem 2. So what Morse theorem 2 states that in the total deflection between any 2 points is equal to the first moment of area. First moment of area. What is the meaning of first moment of area? Area into centroidal distance. You will get the first moment of area between any 2 points that divided by EI. Again, here also In the second theorem also says that whatever the first moment of area of the bending moment diagram you have calculated, divided with EI, you get the total deflection between the any 2 points, right? With this application of these theorems of let us see how to apply these theorems for the case we considered. What is the case we considered? Cantilever beam subjected to point load at its free end, right? Now let us apply. Here you see A x bar. What is x bar? Centroidal distance. Now, so already we have considered this example for the illustration of two methods. Here, my dear friends, let me tell you how to apply Morse theorems or momentary method to find the slope and deflection. So here, how we are going to draw the bending moment diagram? It is very simple. How to draw bending moment diagram? First of all, you have to take a section. How I have taken section here? Section is taken at a distance x from free end. Here it is the section, my section. It is the section. It is taken at a distance x from B. So what is the moment? M equal to, what is the load here? W. What is the distance up to section x? Here this moment produces clockwise moment or anti-clockwise moment. Here this moment produces a clockwise moment with respect to section. Therefore, according to sign convention, put minus. So M equal to minus W x. I hope you understand. Now, I want to find the slope at, bending moment at point B. That means how much value I can put? Put x equal to 0, you are getting bending moment at point B. So substitute the minus W into x is 0. What is the bending moment at point B? 0. Now I want to find the bending moment at the fixed end, that is A. So how much value I can put x? How much value I can put x here? X equal to, so this x will be here, sorry. Here this x will be equal to L. Put x equal to L, you are getting MA. So what is the value you are getting? Minus W into L. So what is this one? Minus WL is a bending moment. Bending moment at point A. What is the bending moment at point B? 0. So you can able to mark the points here. It is a baseline. The blue color is a baseline. Here at point B, what is the bending moment? 0. At a point A, what is the bending moment? WL. The negative sign indicates downward. See? So this is this height indicates WL, right? So this is what is this one? L. Here you understand there is a bending moment diagram obtained, right? Here it is a bending moment diagram for this case. So once you obtain the bending moment diagram, to apply Morse theorem, what you have to do? It is a bending moment diagram. After getting the bending moment diagram, you have to find the area of the bending moment diagram. How to find the area of the bend? What is the shape of the bending moment diagram here? Triangle. So area of the triangle half into, what is the base? That is L into, what is the height here? WL, right? Now, here minus W L square by 2, right? Clear? Area. So, put negative because downward. So, A equal to minus W L square by 2. Now, what is the what is the Morse theorem? Morse theorem 1. It is a change of slope between 2 points. Change of slope between 2 points means here, let me write theta B minus theta A. What is the meaning? It is a slope, change of slope between these 2 points A and B. Theta B minus theta A equal to area of the bending moment diagram by EI. Right? Now theta B minus, what is meaning of theta B? Slope at point B, right? What is theta A? Slope at point A. Already I told you, at the fixed support, what is the slope? 0. So theta B minus 0, you are getting, what is A? Minus W L square by 2 divided by EI. So simplify this, you are get theta B equal to minus W L square by 2 EI. I. Very simple, we are getting the slope at B. Very simple. Two steps we can able to find the slope at point B. So in that case, double integration method, a lot of calculation is there. But in the case of moment area method, we can easily find the slope at point B. So of course, there is a limitation is there. For applying this moment area method, we can apply only for simple cases. Standard cases we can apply. If it is subjected to number of point loads, UDL with different point loads, in such cases, it is highly difficult to apply moment area method, right? Somewhat difficult, right? Now, for your understanding purpose, I will show you typed equations. You can see. After this step is once I understand to apply moment area method, the first step is you have to draw the bending moon diagram. It is our bending moon diagram. So after constructing the bending moon diagram, you have to find the area. You have to find the area. Already I told you how to draw the bending moment diagram. So here, area of the bending moon diagram, it is a triangle. Half into base means this is L, height is WL. So we are getting minus half WL square by 2. So using Morse theorem, what is the Morse theorem here? Change of slope between the points A and B. Net area of the bending moon diagram, net area of the bending moon between the points A and B, right? Now, substitute. Theta B minus theta A equal to A by A. What is that A? Already calculated, right? Minus WL square by 2. So simplify this. Theta A, what is the value of theta A? Theta A is the, why theta A equal to 0? So A point is a fixed support point. Point at the fixed support. Therefore, theta A is 0. Substitute, you are getting theta B equal to minus WL square 2. Already I explained. So this once again I am repeating this, right? Now once you getting the value of slope, the next step is you have to find the deflection. How to find the deflection of this cantilever beam subjected to point load at its free end, right? So here already you have drawn this bending moon diagram. You can see here I am assuming this point is the centroid of this triangle, right? So from the point B, what is the distance of the centroid? This is the total length is L. So from this vertex, how much distance of the centroid? That is 2L by 3, right? Now, what is the to find the deflection, you have to use Moore theorem 2. What is the Moore theorem 2? The net deflection that will be equal to what? Net deflection equal to what? First moment of area. What is the first moment of area? A into x bar by EI, right? Here A, you can find area half into L into WL. You are getting the area. So x bar, what is the x bar? 2L by 3, right? Now, you see this. First moment of area of the bending moon diagram in between the points A and B, right? So first moment of area, you can write area of the bending moon diagram into x bar. So half minus half into L in WL into 2L by 3. What is the 2L by 3 x bar? You are getting minus WL cube by 3. L into L into L. 3L are there. L cube. 2 cancel. Minus WL cube by 3. So it is AX bar. What is AX bar? First moment of area. Right? Now, using the theorem, you can write total deflection between any 2 points. What are the 2 points here? A and B. Right? AX bar by EI. So YB minus YA. YB minus YA equal to minus WLQ by 3. What is this minus WLQ by 3? First moment of area divided by EI. So you are getting YA equal to 0. A point is at a fixed support, right? For at the fixed support, slope equal to 0, deflection equal to 0. Therefore, YA equal to 0. Now substitute YA is 0 there. You are getting YB equal to minus WLQ by 3I. Simple 2 steps, you can find the deflection of the cantilever beam, right? I hope you understand. See. So minus WLQ by 3A. Here, the same expression you got with the help of this with the help of a double integration method. but there is a lot of integration and complexity all are there. But these Morse theorems, by application of the Morse theorems, we can easily find the slope and deflection. Very simple, right? So this is the method of application of the momentary method for finding the slope and deflection of beams. The one of the important limitation for this method is it can be applicable for the simple cases, that means standard cases. So subjected to a UDL, a simple point load, such cases only you can for any beam, cantilever beam or simply supported we can find. The thing is here, what is this beam? It is a simply supported beam. Just I am giving an idea about simply supported beam also. You see, this simply supported beam, what kind of load is acting on it? Here, it is a simply supported beam. Here at A, there is a support, hinged support. At the point B, there is a roller support. Here, there are two supports are there, hinged support and roller support, right? Now, what type of load is acting here? Exactly, there is a point load that is acting at the midpoint of the beam at point C, right? So here, what is this curve line? It is elastic curve. It is an elastic curve. So if I want to get the slope at point A, what I am going to do? Draw a tangent here at point A. Draw a tangent. The tangent makes an angle with the horizontal that give you the slope. Similarly, at point B, if you want to find the slope at point B, you have to draw a tangent here. That gives us angle with the horizontal that gives us slope. Right? What about deflection? Come to the deflection. At supports, already I told you, at supports, what about the deflection? Do you find any vertical distance? No. Here also you can find any vertical distance after load applied? No. Therefore, we can say that deflection at the supports equal to 0. So that means at X, here at left support A, what is the deflection? YA equal to 0. At point B, YB equal to 0, right? Now I want to find the deflection at the point C. I want to find the deflection at point C. So to apply momentary method, the first step is you have to draw the bending moment diagram. It is a bending moment diagram. Here, the important point, my dear friends, you have to draw the bending moment diagram. How much portion you are going to, how much area we are going to consider in between the points. So we are finding the change of slope between A and C, not between A and B, A and C. That's why this area you have to consider. This area you have to consider, right? So how we are going to find this area? This is L by 2. What about this height? WL by 4. So you can able to find the area easily. Half into L by 2 into WL by 4. Like this. WL by 4. You are getting area WL square by 16. So what is the what is the statement of Morse theorem 1? It is the change of slope between the any 2 points equal to area of the bending moment diagram divided by EI, right? Now, with the help of this theorem, with the help of this Morse theorem, we can write theta C minus theta A, because you observe in between A and C, theta C minus theta A. What is the meaning of theta C minus theta A? Change of slope between A and C, right? So that's why I'm taking. So theta C minus theta A, you are getting A by EI, right? Now, what is that A? Already calculated area of the bending moment diagram between the points A and C, not between A and B, between A and C, right? Now, theta C minus theta. What is theta A? Theta A is the slope at one of the supports. So, left support, the hinged support. What is the slope? What is the slope at point A? What is slope at point A? That is 0, right? No. So, not slope. Just let me explain this point clearly. See this, it is your simply supported beam, right? Once it is subjected to a load, at the center, W, say it is L by 2, L by 2. See what kind of shape you can observe after load is applied. Elastic curve takes the curved shape. Let me draw the shape. This one. Here at point A, there is a hinged support, at point B there is a roller support. Wherever the support is there, there itself, what is the deflection? 0. At point A, deflection 0, point B, deflection. But there is a slope is there. Slope is not 0. What is the meaning of slope? At point A, you have to draw a tangent. If there is a curve is there, you draw a tangent like this. So this is the angle made with the horizontal. There is a slope is there. Here at point B, the theta B, it is a slope is there. What about the point C? That means this is a point C. At point C, you draw a tangent. See this? You draw a tangent. Just a minute. Sorry. You see this? At point C, at point C, draw a tangent. You see this? This tangent makes how much angle with the horizontal? Coincides with the horizontal. Therefore, what is the slope? Here 0. At point C, slope is 0. So that's why here point C, theta C is 0. 0 minus theta A equal to equal WL square by 16 EI. So further, you can write theta A equal to minus WL square by 16 EI. So this is the way of finding the slope at A, right? Theta C 0. Theta C this point, not theta A means here. So at the end points, there must be slope, right? No deflection, but there must be slope. At point C, more deflection is there, but slope equal to 0, right? Now, so first moment of area, I'm trying to find the first moment of area. What is the meaning of first moment of area into centroidal distance? So here, see the centroidal distance. So from this, you have to write the centroidal distance. What is the height here? L by 2 now. Now, the height of the triangle is L by 2. So 2 into L by 2h by 3, 2 into L by 2 by 3. So substituting the values, you are getting Ax bar equal to W L cube by 48. So this is the first moment of area considered between the points A and C. So what is the Morse theorem to? The net deflection between the points will be equal to the first moment of area of the bending moment diagram by divided by EI. So substitute the values. So what is y equal to 0? At point A, there is a support. At the support, the deflection equal to 0. Therefore, y equal to 0. So 0 minus yc, that equal to minus WL cube by 48 divided by EI. Further simplify, you will get yc equal to WL cube by 48 EI. So this is the expression for finding the slope at the midpoint of the simply supported beam, right? I hope you understand how to find the slope and deflection of simply supported beam and cantilever beam. So now, my dear friends, what I am suggesting you, you apply the same procedure. You apply the same procedure for finding the slope and deflection of other cases. That means a simply supported beam subjected UDL over the entire span. In the same way you can find the slope and deflection for the cantilever beam subjected to uniform distributed load. So in both the cases, you can follow the same procedure. You can easily find the slope and deflection with the help of moment area method. So you are having some doubt. Suppose there are a beam subjected to number of point loads and UDL are there. In such cases, you don't. I advise you not to attempt these two methods like moment area method or this one double integration method. In such cases, better you can follow Macaulay's method. Any doubts? So if you have any doubts, please feel free to ask me. I will clear all your doubts. I will give a task that you have to adapt these method, momentary methods particularly. You have to apply this method to find the slope and deflection in different cases. That cases means cantilever beam subjected to uniform distributed over the entire span. That is on one case. The another task I am going to give you. One is the simply supported beam subjected to uniformly distributed load over the entire span. So while finding while these two slope and deflection for these cases, if you feel any difficulty, feel free to ask me. I will clarify your doubts. I hope you understand. So let me summarize the today's lecture. So slope and deflection to find deflection are very important for designing the various beams. So for that purpose, you must understand what is slope and what is deflection. So what is the meaning of slope? Slope means in a elastic curve. What is the meaning of elastic curve? Whenever a beam subjected to certain load, it deform a position in the form of a curve. That curve we can call it elastic curve. So wherever you want to find the slope on the slope at a particular on the beam, so the corresponding you have to take the point on the elastic curve. At that point you have to draw a tangent. So whatever the angle made by the tangent with the undeformed position of the beam, that will get the slope. So what about the deflection? The vertical distance between the point on the elastic curve and the undeformed position of the beam. So that will give the deflection. So to find the slope and deflection, there are different methods are there. One is the double integration method. So in the while following double integration method, first you have to take the differential equation of elastic curve. So that is m equal to ei into d square y by dx square. You have to integrate once you are getting the slope equation. Again you are integrating. Double integration means two times integration. Second time integration you are getting the deflection equation. So only the hurdle is there are constants of integration are there, C1 and C2. To find constants of integration, what you have to do? So you have to apply your boundary conditions. So boundary conditions basically depending on the type of the beam. So as far as the cantilever beam is concerned, at the fixed support, both slope and deflection are zero. So you can put these boundary conditions, you can able to find C1 and C2. So in the case of simply supported beam, at the support, so you cannot find any deflection. That means deflection at the supports equal to zero. So with the help of these boundary conditions, we can able to find the slope and find the constants of integration C1 and C2 for the case of simply supported beam. So this is a lot of calculation is there. Integration of mathematical computation is there. So to avoid all these things, there is a simple method, that is a moment area method. So in order to apply moment area method, you first understand the two theorems, Morse theorem 1 and Moore theorem 2. As far as Morse theorem 1 is concerned, so that is theorem particularly pertaining to finding the slope. Theorem 2 is related to finding the deflection of the beam. So as far as Morse theorem 1 is concerned, the change of slope between any 2 points for a beam, that should be equal to the area of the bending moment diagram between those points divided by EI. You are getting the change of slope between the 2 points. Of course, the 2 points, one must be known the value of the slope is 0, right? So in such case, so you can easily find the slope. The other thing is, to find the deflection, you have to use Morse theorem 2. What Morse theorem 2 says? The net deflection between any 2 points is equal to the first moment of area divided by EI. So you have to find what is the meaning of first moment of area? Area into centroidal distance, right? After finding the first moment of area and you have divided with EI, you are getting the directly you are getting the deflection, right? So change of deflection, net deflection. So that's one. Yeah, already I told you at the supports. What is the deflection? That is 0. So with the help of that information, you can able to find the deflection, right? So this is a way of finding the slope and deflection with the help of moment area method. I hope you understand. So what I'm suggesting you have to apply the same procedure to solve the certain numerical problems and certain cases, different cases already. The already one cantilever beam and simple support I told you. So you have to extend the say for the same beams in different kinds of loads. That means uniformly distributed. So I hope you understand. Thank you very much, my dear friends. Thank you very much. If you have any doubts, you call me or you message me or you mail me. Whatever your doubts you are having, I will clarify. Thank you very much, my dear students, my dear friends. Bye. Bye all of you. Bye. Good night.